What if the Big Bang was not a beginning but a reply? Right now, in this moment, photons are bouncing off your retina. Electrons in your fingertips are exchanging quantum states with every surface you touch. And according to one of the most decorated physicists of the 20th century, the man who literally gave us the term black hole, every single one of those interactions is reaching backward across 13.8 billion years of cosmic history, quietly finishing the job of making the universe real, not as a metaphor. As measurable, peer-reviewed, experimentally verified physics, John Wheeler spent the final decades of his career arguing that the universe doesn't just exist, it's still becoming. And in 2007, a lab in France ran the experiment that should have proved him wrong. It didn't. Tonight we're going all the way down into that result, and I don't think you're going to leave with the same picture of reality you walked in with. If you're new here, hit subscribe and get comfortable, because this one's worth every second. Part 1. The universe is still being decided. There is a sentence that most physicists will not say out loud at a dinner party, but that the mathematics of quantum mechanics has been quietly implying for nearly a century now. It goes like this: the past is not finished. Not in some poetic, metaphorical sense. Not in the way a therapist might tell you that your relationship with your childhood is ongoing. In a measurable, experimentally verified, peer-reviewed journal-published sense, the past, as in the actual sequence of physical events that led from the Big Bang to the moment you pressed play on this video, may not have been fully determined when it happened. Some of it may have been waiting for something inside the universe to interact with it, to notice it, to complete it. That is a sentence that should feel wrong. And if it feels wrong to you, that is good, because it means your intuition about reality is functioning normally. It also means your intuition is, at least in part, incorrect. The man most responsible for pushing this idea into the mainstream of serious physics was John Archibald Wheeler. And before we go any further, it is worth pausing on who Wheeler actually was, because this matters. He was not a fringe thinker. He was not the kind of person you find writing self-published books about consciousness and crystals. John Wheeler was one of the most decorated and respected theoretical physicists of the 20th century. He worked on the Manhattan Project. He collaborated with Niels Bohr on the theory of nuclear fission. He was the doctoral supervisor of Richard Feynman, one of the greatest physicists who ever lived, and he was the doctoral supervisor of Hugh Everett, who proposed the many worlds interpretation of quantum mechanics. He coined the term black hole in 1967 at a conference where he used it almost casually, and the term stuck permanently to one of the most important concepts in all of astrophysics. He coined wormhole. He coined quantum foam. The man had a gift for naming the universe's stranger furniture. And then, in the later decades of his career, Wheeler turned his attention to something that made even his colleagues uncomfortable. He started asking what he considered the deepest question in all of physics. Not what is the universe made of, not how did it begin, but how does it exist at all? And his answer, which he spent decades refining and defending, was something he called the participatory universe. The idea that the universe does not exist as a fixed, pre-formed object waiting to be discovered. Instead, it is something more like a process, a continuous act of self-completion. And the thing that completes it is measurement physical interaction. The universe's components interacting with each other, reaching all the way back through cosmic history to define events that happened billions of years before any observer was around to observe them. Now, to understand why Wheeler ended up here, why a man of that caliber spent his final decades arguing something this strange, you have to understand the wound that quantum mechanics left in the foundations of physics. And it is genuinely a wound, not a gap in our knowledge that will eventually be filled, but a structural problem in the theory that physicists have been arguing about for 90 years and have not resolved. Here is the wound. Quantum mechanics, which is the most precisely tested theory in the history of science, its predictions match experiments to 10 decimal places, which is the equivalent of measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. Quantum mechanics says that before you measure a particle, it does not have a definite position. It does not have a definite spin. It does not, in the strictest reading of the mathematics, have most definite properties at all. It exists in what the theory calls a superposition, a combination of all the possible states it could be in, each with a certain probability. And then, when you measure it, when any physical interaction occurs that records or registers one of those properties, the superposition collapses. The particle stops being in multiple states and snaps into one. Here is the word that matters and that people consistently get wrong: measurement. Because the moment you say measurement, most people imagine a scientist in a white coat looking at something through an instrument. They imagine human observation. And that is not what quantum mechanics means. Quantum mechanics does not care about human observers specifically. The theory does not assign any special role to consciousness or intelligence or eyeballs. When physicists talk about measurement in quantum mechanics, they mean any physical interaction that entangles two systems in a way that creates a record, a photon bouncing off an atom, two electrons interacting through their electric fields, a detector registering a particle's position. Any of these count. The universe is constantly measuring itself, in this sense, constantly. At every scale, in every cubic centimetre of space, particles and fields and atoms are interacting with each other. And each of those interactions is a measurement in the quantum mechanical sense of the word. But here is the problem that Wheeler latched onto. Here is the thing that keeps quantum foundations researchers awake at night. If measurement is what completes definiteness, if a particle genuinely does not have a definite position until something interacts with it, then what does that say about the early universe? The universe, before stars formed, before galaxies formed, before planets formed, before life emerged, before eyes evolved, before the first human beings sat upright and looked at the sky, was there a long period during which the universe existed without any interactions that could complete this process? And if so, in what sense was it real? In what sense were those early states of the universe definite? Wheeler's answer was not that consciousness was required. His answer was something even stranger. His answer was that the universe is structured in such a way that observations made now, interactions happening now, this second, in every atom of your body and every photon crossing the room, reach backward through time and participate in defining what happened billions of years ago. That the past is not a sealed record sitting in a vault, that it is, in some physical sense, still being written. And then, in 2007, a team of physicists at the Institut d'Optique in France did an experiment. The experiment was called a delayed choice experiment, and the results came back exactly as Wheeler had predicted 40 years earlier. Individual photons, guided through an optical instrument, adjusted their behavior based on a measurement decision that was made after the photons had already entered the apparatus. After. The word you want to sit with there is after. The decision about how to measure them came after they had already started their journey through the instrument. And yet the photons behaved as if they had always known what measurement was coming, as if the present had rewritten the past. There is no comfortable way to explain this result away. The researchers were not sloppy. The apparatus was not malfunctioning. The random number generator that determined the measurement choice was genuinely random and genuinely operated after the relevant moment in the photon's journey. The result has been replicated, extended to atoms, extended to satellite-based experiments with photons whose paths span thousands of kilometers. The result is solid. Which means the question Wheeler spent his career asking is not a philosophical indulgence. It is a physics question with real experimental content. And the question is this: if the past is not fully determined until it is measured, and if measurement requires something inside the universe to do the measuring, then what completed the universe before there was anything inside it capable of interaction? What made the Big Bang definite? What made the first microseconds of cosmic history real? And Wheeler's answer, the answer we are going to spend this entire video building toward, is the most vertiginous idea in modern physics. He suggested that the universe is, in some physical sense, a self-completing loop, that observers inside the universe participate in defining the universe's own past, that the universe, in the only sense the question can meaningfully be asked, creates itself. That is where we are going. And before we can get there, we need to go back to a disagreement that began over 100 years ago, a disagreement between two men whose names you know, a disagreement that was never really settled, and whose unsettled state is precisely why the question Wheeler asked is still open today. Part 2. The argument that never ended. Niels Bohr and Albert Einstein are the two titans of early 20th century physics, and they disagreed about almost everything that mattered. Not about the mathematics. The mathematics of quantum mechanics, by the time it was fully formalized in the 1920s, was not really in dispute. The equations worked. The predictions were accurate. What they disagreed about was what the equations meant, what the theory was actually saying about the nature of physical reality, and their disagreement was not an academic footnote. It was a fault line that ran through the entire field and that has never, in 100 years, been fully resolved. The reason that fault line matters for our story is that the question Wheeler eventually asked, does the universe create itself through observation, lives directly on top of it. Einstein's position was this. He believed in what philosophers call realism, the idea that there is a physical world out there, existing independently of any observer, with definite properties that the observer does not create, but merely discovers. A particle has a position whether or not you measure it. The moon is there whether or not you look at it. Reality is not contingent on observation. It pre-exists any particular act of measurement, and measurement is simply the process of reading off values that were already there. Einstein found quantum mechanics deeply unsatisfying because the theory, as Bohr interpreted it, seemed to abandon this picture. It seemed to say that a particle genuinely did not have a position before measurement, and Einstein could not accept that. His famous line, "God does not play dice," was his shorthand for this conviction. He was not making a theological argument. He was expressing his visceral refusal to believe that the universe, at its foundation, was irreducibly random and observer-dependent. Bohr's position was harder to state simply, which is actually part of the problem and part of why the argument never got resolved cleanly. Bohr's Copenhagen interpretation of quantum mechanics said, roughly, that it was not meaningful to ask about the properties of a particle before measurement. The question, where is the electron right now, before I measure it, is not a question that physics can or should answer, because there is no fact of the matter. Measurement does not reveal a pre-existing property. It participates in creating the outcome. And when Einstein pushed back, when he designed increasingly clever thought experiments intended to show that quantum mechanics was incomplete, that there had to be hidden variables underneath the quantum randomness that determined outcomes in advance, Bohr would find the flaw in Einstein's arguments and stand his ground. The most important of Einstein's challenges came in 1935 in a paper he wrote with Boris Podolsky and Nathan Rosen. The paper described what we now call entanglement, though Einstein did not use that word. He called it spooky action at a distance, and he meant it as a criticism. The setup is simple to describe. You take two particles and allow them to interact in a specific way so that their quantum states become correlated. Then you separate them, send one to one side of the lab and one to the other. Now you measure the spin of one particle. Instantly, the other particle's spin is determined, even though they are separated in space, and no signal could have traveled between them in time. Einstein's argument was that this was absurd. It violated the principle that no influence could travel faster than light, and therefore quantum mechanics had to be incomplete. There had to be some pre-existing agreement between the particles, some hidden instruction they shared before they were separated, that determined the outcome in advance. For 30 years, that debate was essentially philosophical because there seemed to be no way to test it. Then, in 1964, an Irish physicist named John Bell published one of the most quietly devastating papers in the history of science. Bell's theorem was a mathematical proof that showed that if Einstein was right, if particles carried hidden, pre-programmed instructions that determined their measurement outcomes in advance, then certain statistical correlations between measurements on entangled particles could not exceed a specific numerical limit. The number became known as Bell's inequality. And Bell showed that quantum mechanics predicted violations of that inequality. Quantum mechanics predicted correlations stronger than any hidden instruction set could produce. The experiments to test this were done beginning in the 1980s, most famously by Alain Aspect and his team in Paris, and have been repeated and refined ever since. The most rigorous tests, which closed all the remaining technical loopholes, were done in 2015 by 3 independent groups simultaneously. The results were unanimous. Bell's inequality is violated by exactly as much as quantum mechanics predicts. Einstein's version of reality, a world with definite pre-existing properties, independent of observation, explained by hidden variables, is experimentally ruled out. That is not a philosophical conclusion. That is an experimental result. The universe does not behave as if particles have definite hidden properties before measurement. Einstein was wrong. And the reason this matters for the central question we are asking tonight is that it closes a door. If hidden variables were the answer, if there were some underlying level of reality where particles had definite positions and spins before anyone measured them, then the measurement problem in quantum mechanics would be solvable without doing anything radical to our concept of reality. You would not need Wheeler's participatory universe. You would not need any of the strange machinery we are going to explore. The universe would have a definite history, independent of observation, and the question of what completed the early universe would have a simple answer. It was always complete. Bell's theorem says no, that door is closed. And here is the crucial follow-up. Bohr's Copenhagen interpretation, which won the battle against Einstein, does not actually resolve the problem either. Copenhagen says measurement creates definite outcomes, but it does not say what measurement is exactly. It does not explain when a superposition collapses. It does not tell you how the transition from quantum indeterminacy to classical definiteness happens. It just says it does when a measurement occurs, and draws a line between the quantum and classical worlds without explaining the line. This is sometimes called the measurement problem, and it is still open. It has been open for nearly 100 years, so we are left in a strange position. Einstein's reality is ruled out. Bohr's interpretation works, but leaves a gaping hole where the explanation should be. And sitting in that hole is the question Wheeler spent his career trying to answer. If measurement completes reality, and if the universe is full of things completing each other through interaction, then maybe the universe's completion of itself is not an external act, but an internal one. Not something that happens to the universe from outside, but something the universe does to itself from the inside. The Bohr-Einstein argument did not end. It just opened the door to something stranger than either of them intended. Part 3. The first crack in reality. In 1935, The same year, Einstein published his entanglement paradox. An Austrian physicist named Erwin Schrödinger sat down and wrote a thought experiment that he intended as a reductio ad absurdum. He wanted to show how ridiculous the implications of quantum mechanics were if you took them seriously at macroscopic scales. Instead, he accidentally created the most famous image in the history of physics, and the problems he was trying to mock are still unsolved today. You know the thought experiment. A cat is placed in a sealed box with a vial of poison connected to a Geiger counter monitoring a radioactive atom. If the atom decays, the counter triggers a mechanism that breaks the vial and kills the cat. If the atom does not decay, the cat lives. Quantum mechanics says the atom is in a superposition of decayed and not decayed before you open the box. The standard interpretation of quantum mechanics says that superposition should extend to everything connected to the atom, the counter, the mechanism, the vial, and yes, the cat. So before you open the box, the cat is, according to the mathematics, in a superposition of alive and dead. Schrödinger found this conclusion absurd. A cat is a large, warm, biological organism with a definite state. It is not like an electron. It is not reasonable to say it is simultaneously alive and dead. And that absurdity was his point. He was trying to illustrate that the standard quantum mechanical treatment of measurement and superposition could not possibly be the whole story. There had to be something that explained when quantum weirdness stopped applying and classical definiteness took over. There had to be a mechanism for collapse. But here is the thing. 100 years later, we still do not have that mechanism. And the more seriously physicists have taken the thought experiment, the more the absurdity has migrated upward rather than downward, not from the quantum world to the cat, but from the cat to the physicist opening the box. Because if you take quantum mechanics seriously, consistently, without drawing an arbitrary line anywhere, then the physicist who opens the box also becomes part of the quantum system. When the physicist looks at the cat, the physicist's brain enters a superposition of the state in which it observed a live cat and the state in which it observed a dead cat. And if someone else is watching the physicist through a window, their brain enters a superposition too. The chain never ends. This extension of the thought experiment was made explicit by Eugene Wigner, one of the great physicists of the mid-20th century. Wigner proposed what is now called the Wigner's friend scenario. Imagine a physicist, Wigner's friend, is inside a sealed laboratory conducting a quantum measurement. According to quantum mechanics, from the perspective of an observer outside the lab, Wigner himself, standing in the hallway, the entire inside of the lab, including the friend and the measurement apparatus, is in a superposition until Wigner himself makes a measurement. But from the perspective of the friend inside the lab, collapse has already occurred. The friend got a definite result. The friend's reality is definite. Wigner's reality, from outside, still has the friend in superposition. Both descriptions are valid within quantum theory. There is no contradiction in the mathematics, but they are physically inconsistent with each other. One observer has a definite outcome. Another observer, equally valid, has a superposition. Which description is correct? The theory does not say. And for decades, this was considered an interesting puzzle, but not a catastrophic one, because it seemed like a thought experiment you could not actually perform. Then, in 2018, a pair of theoretical physicists named Daniela Frauchiger and Renato Renner published a paper that formalized the Wigner's friend problem and extended it to a scenario involving multiple observers and multiple measurements. What they showed was stark. If you assume that quantum mechanics applies universally at all scales, not just to particles, but to observers and labs and everything else, and if you assume that different observers can each trust the predictions of quantum mechanics from their own perspective, and if you assume that facts about measurement outcomes are absolute and not observer-dependent, then you get a logical contradiction. You get a situation where two observers, each using quantum mechanics correctly, arrive at mutually contradictory conclusions about what happened. This is not a philosophical quibble. This is a theorem. And what it says is that at least one of those three assumptions must be wrong. Either quantum mechanics does not apply universally, or observers cannot fully trust quantum mechanics as a predictor of others' experiences, or the facts about measurement outcomes are not absolute. They are relative to the observer who measured them. 2 years later, in 2020, a team of experimentalists led by Kokwei Bong published results from an experiment designed to test this framework. What they were probing was something they called local friendliness, a set of conditions that any theory with both quantum mechanics and observer-independent facts about measurement outcomes would have to satisfy. Their results showed a violation of those conditions. The universe, when pushed to the limit of what it is forced to reveal about itself, does not behave as if measurement outcomes are globally consistent facts that every observer must agree on. Reality, at the level where quantum mechanics operates, may genuinely be observer-dependent. Now, this is the moment in the conversation where the temptation is to reach for one of the popular rescue packages. Maybe this just means we need a better interpretation of quantum mechanics. Maybe many worlds solves this. Maybe decoherence explains it. We are going to look at all of those options. But for right now, the important thing is not which rescue package you prefer. It is to feel the weight of what these experiments are saying. They are not saying that consciousness creates reality. They are not saying that you can think positive thoughts and make good things happen. They are saying something much more precisely unsettling. The concept of a single, globally consistent, observer-independent physical reality is not supported by the experimental data. The universe, at the level we can most carefully probe it, does not behave as if reality is a pre-existing object with fixed properties that observers simply read off. It behaves as if the act of measurement, physical interaction, entanglement, the registering of information is part of what constitutes reality itself. Which brings us straight back to the central question. If reality is completed by measurement, and if the universe at its earliest moments was an almost unimaginably hot, dense, undifferentiated plasma in which the interactions we are describing were happening everywhere at once, then the question is not whether measurement matters. The question is what the chain of measurements looks like when you follow it all the way back. What was at the beginning of the chain, and is there any physical sense in which the chain loops back on itself? Wheeler thought there was, and to understand why, we need to understand his three most important ideas. Ideas he spent decades developing. Ideas that most of his colleagues found uncomfortably close to the edge of what physics is supposed to say. We need to understand what Wheeler meant when he said the universe participates in its own creation. And to do that, we need to start with the most dangerous idea he ever had. Part 4. Wheeler's most dangerous idea. John Wheeler was, by all accounts, a man who relished the provocative question, not for the sake of controversy, but because he genuinely believed that the deepest questions in physics were the ones that most threatened your basic assumptions about what questions you were allowed to ask. He had a phrase for the kind of question he was after, the question behind the question. Not what is matter made of, but why does anything exist to be made of anything at all? Not how does the universe expand, but why does it have the kind of structure that permits expansion to be a meaningful concept? By the 1970s, Wheeler had begun publicly developing what he called the participatory universe. And to understand what he meant, and to understand why this is not mysticism, but a genuine physical conjecture with testable implications, you need to understand the intellectual journey that got him there. Wheeler had spent decades working at the intersection of general relativity and quantum mechanics. These are the two greatest theories in modern physics, and they do not agree with each other. General relativity describes gravity as the curvature of space-time and works with extraordinary precision at large scales, planets, stars, galaxies. Quantum mechanics describes the behavior of particles and fields at small scales and also works with extraordinary precision. When you try to combine them, when you try to describe what happens at the scale where both are relevant, like the center of a black hole or the first instant of the Big Bang, the mathematics breaks down. You get infinities, you get nonsense. This is one of the great unsolved problems in theoretical physics. Wheeler believed that the resolution of this problem would not come from a technical fix, it would come from a conceptual revolution. He believed that physicists were making a hidden assumption that needed to be challenged, the assumption that the universe was built from physical stuff, particles, fields, space-time, geometry. Stuff that existed as stuff, with properties, whether or not any other part of the universe interacted with it. Wheeler thought this assumption was wrong. He thought the universe was not fundamentally made of stuff. He thought it was made of information. And he gave this idea a name that has stuck. It from bit. Physical existence, the it, arises from binary information, the bit, from yes or no questions, from answers. To explain what he meant, Wheeler used an analogy he called the game of 20 questions but with a twist. You know the standard game. One player thinks of something and the other players ask yes or no questions to narrow it down. Wheeler's version starts the same way, but the player who supposedly thought of something actually has not decided anything in advance. Each answer must merely be consistent with all the answers given so far. By the end of the game, the object has been brought into existence by the sequence of constrained answers, not recalled from a pre-existing decision. The object was not there until the questions defined it. Wheeler's claim was that the universe works this way. Physical reality is not a pre-existing object with definite properties. It is the accumulated output of all the yes or no interactions, all the measurements, in the quantum mechanical sense, that have ever occurred within it. Each interaction is a question asked of reality. Each outcome is an answer. And the accumulation of those constrained answers is what we call the physical world. The universe, in this picture, is not a noun. It is a verb. It is the ongoing process of questioning itself into existence. This connects directly to the question at the center of everything we are discussing tonight. If reality is constituted by interactions by measurements, then the question of what the universe was like before any measurements had occurred is not just philosophically puzzling, it is physically problematic. Because in Wheeler's framework, asking what the universe was like before it had been questioned into any definite state is like asking what the answer was before anyone asked the question. There is no answer. There is only the process of answering. But Wheeler went further than this. He did not just claim that the present universe is constituted by its measurement history. He claimed that observers in the present, including us, participate in defining events in the cosmic past. He drew a famous diagram that he called the U-shaped universe. Imagine the letter U. The bottom of the U is the Big Bang, the earliest moments of the universe. The two arms of the U stretch upward, representing the evolution of the universe through time. At the top of one arm are observers, us, now. And Wheeler drew an eye at the top of the U, looking backward and downward, all the way to the bottom, all the way to the Big Bang. The eye, through the act of observation, participates in defining what happened at the bottom of the U. The observer at the top completes the universe at the bottom. The universe, in this picture, is shaped like a loop. Its end participates in its beginning. It is, in some physical sense, the cause of itself. This is an extraordinary claim. And Wheeler knew it. He spent the later part of his career trying to find an experiment that could actually test whether past events could be influenced by present measurement choices. and he designed exactly such an experiment, the delayed choice experiment. The setup was clear, the logic was tight, and Wheeler proposed it in 1978. It took another 29 years for technology to advance to the point where it could be performed with sufficient precision to be definitive. But when it was, the results came back the way Wheeler said they would. Part 5. The Delayed Choice Experiment. To understand what the delayed choice experiment actually tests, you need to understand a piece of apparatus called the Mach-Zehnder interferometer. It sounds technical, but the principle is simple, and it is one of the most beautiful demonstrations in all of experimental physics. Imagine a photon, a single particle of light. It encounters a beam splitter, a half-silvered mirror that reflects 50% of incoming light and transmits the other 50%. A single photon, encountering this beam splitter, can, in principle, go either way, reflected or transmitted. In the classical picture, we would say it randomly goes one way or the other, 50-50. But that is not what happens. What actually happens is that the photon enters a superposition of both paths simultaneously. It goes both ways at once. This is not an interpretation or a philosophical claim. It is demonstrated directly by what happens next. After the photon splits, the two paths are redirected by two ordinary mirrors so that they converge on a second beam splitter. If the photon had only gone one way, if it had behaved classically and taken a single path, then when it hit the second beam splitter, it would again have a 50-50 chance of going toward either of two possible detectors. You would see roughly equal counts at both detectors over many trials. But that is not what happens. What happens is that the photon, having taken both paths simultaneously as a wave, arrives at the second beam splitter as an interference pattern. The two paths interfere with each other. Depending on the exact path lengths, the photon ends up at one specific detector essentially 100% of the time. The interference is that clean. This is wave behavior. The photon, traveling through the apparatus, behaves as a wave, spreading through both paths and interfering with itself. Now, here is where it gets interesting. Suppose you add a detector to one of the paths, some device that can tell you which path the photon took. The moment you do this, the interference disappears. The photon now behaves as a particle. It went one way or the other. No superposition, no interference. You can have wave behavior or particle behavior, depending on whether you measure which path the photon took, but you cannot have both. Richard Feynman called this the central mystery of quantum mechanics. In 9 words, this experiment contains everything strange about quantum mechanics. The photon's nature, wave or particle, is determined by how you set up the measurement. It is not that the photon is secretly a wave or secretly a particle, and you just do not know which. The photon's behavior is genuinely different depending on the measurement context. Now here is Wheeler's twist. What if you delay the choice? What if you set up the apparatus so that the photon has already entered the beam splitter, already begun its journey through the apparatus, and then, after it is already in flight, you decide whether to insert the second beam splitter or not? If you insert it, you get wave behavior interference. If you remove it, you get particle behavior one path, no interference. The question is, does the photon's behavior change based on a decision made after it has already started? And the answer, when the experiment was done by Vincenzo Jacques and his team in 2007, was yes. The team used a quantum random number generator, a device that generates genuinely random choices based on quantum noise to decide whether to insert or remove the second beam splitter after the photon had already passed the first one. The decision was made while the photon was, in light travel time terms, already inside the apparatus. There was no time for a signal to travel from the decision point back to the photon's starting position. And yet, across thousands of trials, the the photon's behavior at the detectors matched perfectly with whichever configuration had been chosen. Wave behavior when the second beam splitter was present. Particle behavior when it was absent, every single time. Let us be precise about what this is not saying. It is not saying that information traveled backward in time. It is not saying that the future caused the past in a simple causal sense. It is not giving you a mechanism for sending messages to the past. The random number generator's choice cannot be controlled, so no usable information is transmitted. What it is saying is something subtler and in some ways more unsettling. The photon's behavior in the past was not determined until the measurement was made in the present. The past, in this sense, was undecided. It had not fully committed to one mode of existence. It was, if you insist on taking the mathematics seriously, in a superposition of wave-like and particle-like histories, and that superposition was resolved by a measurement decision made after the fact. Since 2007, the experiment has been extended and refined. Researchers have done versions with atoms instead of photons, showing that the effect is not limited to massless particles. Experiments using light from distant stars, with photons that have been traveling for hundreds or thousands of years, have been proposed and partially implemented. The cosmic version, which we will get to shortly, is conceptually the most staggering application of the principle. In 2017, a team used light from quasars, located billions of light years away, to set the measurement choices in a Bell test experiment, trying to ensure that the hidden variable loophole could not be exploited even across cosmological distances. The results continued to violate Bell's inequality. The universe continued to refuse to pre-commit. The key conclusion, the one that matters for the question we started with, is this: the past is not a fixed, sealed record. The behavior of a physical system in the past is not fully determined independently of how it will eventually be measured. And if that is true for a photon passing through a tabletop apparatus over a distance of a few meters in a few nanoseconds, then it is, in principle, true across any scale, including the cosmological scale that Wheeler was thinking about when he proposed the idea, including the scale of the entire universe from the Big Bang to now. Which means the question Wheeler was asking is not rhetorical, it is not metaphor, it is physics. What completed the universe's early history? What resolved the superpositions of the primordial cosmos? And Wheeler's answer was, we did. Not just us, every interaction in the universe's history, but including us, including now. Including the photons bouncing off the page you are reading, or the screen you are watching right now, adding their small increment to the universe's ongoing self-definition. Part 6. The Quantum Eraser. If the delayed choice experiment shook your confidence in the fixedness of the past, the quantum eraser is going to do something worse. It is going to show you that even after a particle has been detected, even after it has apparently left a definite result, the pattern that result belongs to can still be changed by a measurement that happens later. The setup involves a slightly different apparatus and a concept called entanglement. You take a special kind of crystal. There are several kinds that work, but the physics in all of them is the same, and you fire photons through it. The crystal, through a process called spontaneous parametric downconversion, sometimes takes one incoming photon and converts it into two outgoing photons with lower energy. These two outgoing photons are entangled. Their quantum states are correlated in a way that cannot be explained by any pre-existing shared information, as Bell's theorem tells us. One photon is called the signal photon. It goes toward a detector and arrives there first. The other photon is called the idler photon. It is sent on a longer path toward a different part of the apparatus. The important thing is the timing. The signal photon is measured first. Then, later, a choice is made about what to do with the idler photon. Here is what happens depending on that choice. If the idler photon is measured in a way that preserves which path information, that is, in a way that, in principle, tells you which path the signal photon took, then the signal photons, when you look back at their detection pattern, show no interference. They distributed across the detector screen the way particles would, with no wave-like bands. Now you make the other choice. You measure the idler photon in a way that erases which path information. The measurement on the idler is designed so that it is physically impossible, even in principle, to reconstruct which path the signal photon took. And when you look back at the signal photon detections that correspond to those erased idler measurements, when you sort the signal detections by which category of idler measurement they match, you see interference. The interference pattern is there, present in a subset of the already recorded data, appearing only when you sort by the later measurement outcome. The signal photons have already been detected before the idler photons are measured, and yet the pattern the signal photons form, whether they show interference or not, depends on what is done with the idler photons afterward. Now, there is a critically important clarification to make here, because this experiment is one of the most consistently misrepresented results in popular science communication. The quantum eraser does not allow you to send information backward in time. It does not allow you to change the past in any operationally meaningful sense. The reason is that you cannot see the interference pattern just by looking at the signal photons alone. If you look at all the signal detections together, undivided, they show no interference. They look like particles. The interference only emerges when you subdivide the signal detections according to the later idler measurements, a process called coincidence counting. And to do that coincidence counting, you need the later measurement results, which you can only get after the idler measurements are made, so no information is transmitted backward. The interference pattern in the past signal photons cannot be used to send a message, because you cannot see it without information from the future idler measurements. But, and this is the but that matters, what the experiment shows is that the completeness of the past event is genuinely entangled with a future measurement. The signal photons do not have a definite, complete story until the idler measurements are made. The correlations between past and future are real, not illusory. The past event and the future measurement are bound together in a way that is not explained by any local hidden variable. Bell's theorem guarantees that. The universe, it turns out, does not seal its records as it goes. It keeps them partially open, pending the outcomes of future interactions. It is as if the universe is maintaining a kind of ledger in which entries from the past can only be fully finalized by reconciling them against entries from the future. This connects directly back to the central question we are building toward all night. Wheeler's participatory universe claims that the chain of measurements, interactions that complete quantum states extends all the way from the present back to the Big Bang. The quantum eraser shows that even after a photon has been detected, its past history is not independent of subsequent measurements on its entangled partner. Extend that logic to the cosmic scale, and what you get is something that looks very much like what Wheeler was describing. A universe whose past is not a finished document, but a constrained draft that continues to be finalized through every interaction occurring now. The question is, what happens when you scale this up from a tabletop experiment to the universe itself? And for that, you need a quasar, a gravitational lens, and several billion years of light travel time. Part 7. The cosmic version. There is a class of objects in the sky called quasars, quasi-stellar objects. They are among the most energetically extreme things the universe contains. The centers of active galaxies, where supermassive black holes are actively consuming surrounding matter and releasing, in the process, more light per second than an entire galaxy of hundreds of billions of stars. Some quasars, are so far away that the light we receive from them left its source when the universe was less than 1 billion years old. When you observe a quasar, you are not just looking at a distant object. You are looking at an event from the early universe, one that your telescope is completing, in the quantum mechanical sense, right now. Wheeler's cosmic version of the delayed choice experiment involves not a lab apparatus, but a gravitational lens. Gravitational lensing is the phenomenon predicted by general relativity, in which a massive object, a galaxy, a cluster of galaxies, bends the path of light passing near it. If a quasar is located far behind a massive galaxy from our perspective, the galaxy's gravity bends the quasar's light around it, and we see multiple images of the same quasar, one on each side of the lensing galaxy. These are separate images produced by light that took different paths around the lens. But here is the crucial thing. Those are not just different beams of light. They are two paths through which the same photons could have traveled. In the quantum mechanical picture, a photon from the quasar does not choose which path to take. It is in a superposition of both paths simultaneously wave-like until a measurement is made that determines which path it took. And here is where Wheeler's thought experiment becomes staggering in its implications. You can set up a detector arrangement in the same way as a Mach-Zehnder interferometer, using the gravitational lens as the equivalent of the first beam splitter and a telescope arrangement as the second. If you configure your telescope to allow the two paths to recombine and interfere, you get wave behavior. The photon took both paths simultaneously. If you configure it to determine which path the photon took, you get particle behavior. The photon took one specific path. And the choice of which configuration to use the measurement decision that determines wave or particle behavior is being made now, today, in the telescope. While the photons that were emitted by that quasar have been travelling for billions of years, Wheeler's conclusion from this thought experiment was explicit. When we make the measurement choice now, we are in some physical sense determining the behavior of those photons during their billion-year journey. We are retroactively influencing whether those photons took one path or two paths through a gravitational lens that itself might be located 8 or 10 billion light-years from Earth. The present, through the act of measurement, is participating in defining the past across the entire observable universe. The most ambitious observational test of this idea was done by a team including Anton Zeilinger, one of the people most responsible for the experimental development of Bell test physics, who later won the Nobel Prize for exactly this kind of work. In 2017, a collaboration used light from distant quasars' photons that had been travelling for about 8 billion years to set the measurement choices in a Bell test, choosing which measurements to perform based on the colour of quasar photons received just before the entangled particle measurement was made. The idea was to push the hidden agreement window as far back in time as possible to show that even if particles had been pre-programmed with hidden instructions, those instructions would have to have been set at least 8 billion years ago, when the quasar light was emitted, for the results to be explainable without quantum correlations. The results violated Bell's inequality. The universe continued to refuse to behave as if its outcomes were preset. There is a diagram Wheeler used to illustrate all of this that is worth spending a moment with, because it captures, in a single image, the central claim of everything he spent his later career arguing. He drew the universe in the shape of a U. At the bottom of the U is the Big Bang, the earliest moments of cosmic existence. The two arms stretch up and outward through time, representing the universe expanding and evolving over 13.8 billion years. At the top of the right arm is an eye, an observer. That eye is looking back down through the apparatus of observation, telescope, instruments, the chain of physical interactions that constitutes any measurement all the way to the bottom of the U. And Wheeler drew an arrow from the eye back to the Big Bang. the observer's measurement, reaching back across all of cosmic time, the universe completing its own origin through the act of observation within it. This is not a metaphor for Wheeler. It is a literal physical claim. The universe at its beginning was in a superposition of states. The interactions within the universe, every measurement made by every physical system progressively resolve those superpositions. And the cumulative effect of all those resolutions all the way back is that the universe becomes definite. It becomes fully real. And it does so through its own internal interactions. It creates itself. But to take that claim seriously, to decide whether it is physics or poetry, you need to grapple with the deeper question it raises. If the universe is made of information, if reality is constituted by measurement, if observation reaches backward through time, what does that say about the fundamental nature of space, time, and physical existence itself? And this is where we have to go somewhere that even Wheeler did not fully anticipate, the idea that space and time themselves are not fundamental features of the universe, but emergent structures that arise from something deeper, something informational. Part 8 It from Bit. In 1972, a 25-year-old graduate student named Jacob Bekenstein was working in John Wheeler's group at Princeton when he proposed an idea that his supervisor found initially implausible and that the rest of the physics community found outright outrageous. Bekenstein suggested that black holes have entropy thermodynamic disorder proportional to the area of their event horizon. This was outrageous for multiple reasons. Entropy is a property of matter in thermal equilibrium. Black holes, by definition, let nothing out. How could something that let nothing out have thermodynamic properties? And more troublingly, if black holes had entropy, they also had temperature, which meant they had to radiate, which was flatly impossible for a system that trapped everything within its event horizon. Then Stephen Hawking did the calculation that showed Bekenstein was right. In 1974, using a combination of general relativity and quantum field theory, Hawking showed that black holes do radiate. They emit a thermal spectrum of particles now called Hawking radiation at a temperature inversely proportional to their mass. And the entropy of a black hole is indeed proportional to its surface area, not its volume. For every 4 square Planck lengths of event horizon area, where a Planck length is about 1.6 times 10 to the minus 35 meters, the smallest meaningful length scale in physics, a black hole has exactly 1 bit of entropy, 1 bit per 4 Planck area units. The reason this matters enormously for our story is what it implies about information and physical reality. In ordinary physics, the entropy of a system, the amount of information needed to fully describe its microstate, scales with its volume. A box of gas, twice as large, needs twice as much information to describe. But for a black hole, the information content scales with area, not volume. The 3-dimensional interior of a black hole is completely described by information encoded on its 2-dimensional surface. The volume is, in some sense, redundant. The surface is what is fundamental. This observation that a 3-dimensional physical system can be completely described by information on a 2-dimensional boundary is the basis of the holographic principle. And the holographic principle, developed in the 1990s through work by Gerard Hooft and Leonard Susskind, says something radical about the nature of space itself. It suggests that the 3-dimensional world we perceive might not be the fundamental reality. It might be a kind of projection, like a hologram, from information encoded on a lower dimensional boundary. The most concrete and technically developed realization of this idea is a correspondence discovered by Juan Maldacena in 1997, known as ADS, CFT. The initials stand for anti-de Sitter space and conformal field theory. The specifics are technical, but the conceptual content is this. Maldacena showed that a gravitational theory in a certain kind of curved 3-dimensional space is exactly equivalent, in all its physical predictions, to a quantum field theory with no gravity operating on the two-dimensional boundary of that space. The two theories are dual to each other. Every physical fact about the three-dimensional gravitational system has an exact counterpart in the two-dimensional non-gravitational theory. This is not a speculation. It is a duality that has been checked extensively, and while it has not been proven in full mathematical generality, it has been verified in enough detail that most theoretical physicists treat it as essentially correct. And its implication for the nature of reality is striking. Gravity, the curvature of space-time, the geometry of three-dimensional space is not fundamental. It emerges from quantum information processing on a boundary. Space-time is not a stage on which physical events happen. It is something that emerges from something more fundamental, something informational. Wheeler's "it from bit," his claim that physical reality arises from information, is not a philosophical slogan in this context. It is an active research program with increasingly concrete mathematical implementations. The idea that physical existence, including space and time themselves, is constituted by information and its processing is not fringe speculation. It is the direction that a significant portion of theoretical physics has been moving for 3 decades. And it connects directly to the central question we are asking. If space-time is emergent from information, if physical reality is constituted by the outcomes of binary interactions, then the question of what the universe was like before information began to be processed within it is not a question about a prior physical state. It is a question about a prior informational state. And an informational state that has not been processed, has not been measured, has not been interacted with, has no physical content. It is, in the most literal sense, nothing. Wheeler's claim that the universe creates itself is, in this informational picture, not mystical. It is almost tautological. A universe constituted by information processing cannot predate its own information processing. The universe is the information. The information is the universe. And the act of processing that information, every measurement, every interaction, every collision of particles, is the act of creation. Part 9: Space and time are not fundamental. Here is a question that sounds almost embarrassingly simple until you actually try to answer it with any precision. What is time? Go ahead. Try it. Not in a poetic sense, not time is the great river or time is the measure of change. In a scientific sense. What is time as a physical thing that we could in principle point to? Your intuition has an immediate answer, and the answer feels so obvious it barely registers as an answer at all. Time is the thing that flows. It is the dimension along which events are arranged. The past is behind you, the future is ahead of you. The present is where you are right now reading this sentence, which is already receding into the past while a new present rushes in to replace it. This is so self-evident that you have probably never seriously questioned it. Time is just the river you are floating on. Everyone knows this. Here is the problem. Quantum mechanics and general relativity, the two greatest and most precisely verified theories in the history of physics, when you push them into honest dialogue with each other, both point quietly toward the same uncomfortable conclusion. The river might not be real. Time, as a fundamental external framework in which physical events are embedded like pearls on a string, may not be fundamental at all. It may be something that emerges. Something that the universe manufactures from the inside, from relationships between its parts, rather than something the universe is sitting inside of. And if that is true, if time is not a container that the universe inhabits, but a product that the universe generates, then the question, what happened before the universe began, may not be unanswerable, because we lack data. It may be unanswerable because the question contains a hidden assumption that doesn't survive contact with physics, that there was a before, that the universe was preceded by a time in which it did not yet exist, and then something caused it to appear. That logic requires an external timeline, a stage already set, already ticking, on which the universe's origin could be located. And if that external timeline doesn't exist, then the question dissolves. Not because we give up on it, but because the universe, very politely and with complete mathematical rigor, tells us we're asking the wrong thing. Let's build this slowly, because it deserves to be built slowly. The argument starts with entanglement. By this point in our story, we've talked about entanglement as a strange correlation between particles across space. Two particles, separated by any distance, sharing quantum states in a way that no classical hidden variable can explain. Einstein hated it. Bell's theorem ruled out the alternative. The experiments confirmed the weirdness. Fine, we've accepted the spatial strangeness of entanglement. But in the 1970s, two theorists named Don Page and William Wouters, and I want to say their names clearly because they do not get nearly enough credit in popular physics, proposed something even stranger. They suggested that entanglement might also explain the emergence of time itself. Not time as a correlation across space, time as the experience of sequence, of before and after, of change. Their mechanism is now called the Page-Wouters mechanism, and the core idea is one of those things that sounds wrong until it suddenly sounds like the only thing that could possibly be right. Here is how it works. Consider a universe, not our universe specifically, just a universe in general, described by a quantum state. If that universe obeys the Wheeler-DeWitt equation, which is quantum mechanics' best attempt at describing gravity, the quantum analog of the equation that governs how quantum states evolve, then a very strange thing follows. The total quantum state of the universe, viewed as a whole, does not change. It is static, timeless. From the outside, if there were an outside, which there isn't, but let's say there were, the universe would look frozen, no evolution, no dynamics, just a single fixed quantum state, hanging there, unchanging. This is sometimes called the problem of time in quantum gravity, and it is one of the genuine deep puzzles in theoretical physics. If the equation governing the universe says the universe doesn't evolve, how does anything happen? How are we here, experiencing change, experiencing one moment following another? The Page-Wouters answer is subtle and beautiful. From the outside, yes, the universe is static, but nobody is on the outside. Everything is inside. And inside that static universe, subsystems are entangled with each other. A clock, meaning any physical system that evolves through a sequence of distinguishable states, a swinging pendulum, a decaying atom, a spinning particle, is entangled with the rest of the universe. And from the perspective of an observer also inside the universe, also entangled with that clock, something remarkable happens. The clock appears to tick. The rest of the universe appears to change relative to the clock. Not because time is flowing, but because the quantum correlations between the clock and everything else, seen from inside the entanglement, look exactly like the passage of time. Time, in this picture, is not a river you're floating on. Time is what entanglement looks like from the inside. For decades, this was a beautiful theoretical idea with no direct experimental analogue. Then, in 2014, a team led by physicist Ekaterina Moreva did something that should have made much bigger headlines than it did. They took two entangled photons. One photon played the role of the clock. The other played the role of the rest of the universe. They then arranged two kinds of measurements. The first was an external observation, someone measuring both photons simultaneously, from outside the entangled system. That observer saw no evolution. The system looked completely static. Time was not happening. The second was an internal observation, someone using the clock photon as a reference to measure the other photon. That observer saw evolution. They saw the other photon changing, shifting, moving through states in a way that looked precisely and quantitatively like the ticking of time. Two photons, one static from outside, evolving from inside. Time as an artifact of perspective within entanglement. I want to be careful here, because this is a small experiment and I don't want to oversell it. Two photons is not a universe. The analogy is not perfect. But the principle it demonstrates is real and it matches the mathematics. Time, as an experience phenomenon, does not require a clock outside the universe. The universe can generate the experience of time entirely from internal quantum correlations. The timekeeper is inside. The clock is part of the system it's measuring. And somehow, against all intuition, that works. Now, hold that thought, and let's add the second piece. In 2010, a Canadian theoretical physicist named Mark van Ramsdonk published a paper that has since become one of the most discussed in theoretical physics, and one of the most consequential for how physicists think about space itself. Van Ramsdonk was working within the ADS CFT framework, the correspondence we talked about earlier, where a gravitational theory in 3 dimensions is exactly equivalent to a quantum field theory on a 2-dimensional boundary. And he showed something that, if you sit with it long enough, starts to feel like it should have been obvious and also like it fundamentally cannot be true. He showed that space is held together by entanglement. Specifically, the geometry of space, the fact that 2 regions of space are nearby or connected, corresponds precisely to the degree of quantum entanglement between the quantum systems associated with those regions. On the boundary, 2 regions that are highly entangled in the quantum description are geometrically close in the 3-dimensional description. 2 regions with low entanglement are far apart. 2 regions with no entanglement at all are disconnected. There is no space-time path between them. The spatial fabric itself, the connectivity of the universe's geometry, is encoded in quantum correlations. Reduce the entanglement, and space doesn't just stretch, it tears. It splits into separate disconnected islands of space-time with no route between them. Van Ramsdonk showed this with an actual calculation, not just a metaphor. In the ADS CFT correspondence, the math is explicit. Entanglement holds space together. Space is woven from quantum correlations. And if that wasn't enough, in 2013, Juan Maldacena and Leonard Susskind took this a step further with what is now called the ER equals EPR conjecture. The notation refers to 2 papers Einstein published in the same year, 1935, which was apparently a banner year for ideas that would take a century to fully unpack. Refers to the Einstein-Rosen paper, which described wormholes, theoretical tunnels through space-time connecting 2 distant regions. EPR refers to the Einstein-Podolsky-Rosen paper, which described entanglement. These 2 things, written in the same year by the same man, about apparently completely unrelated topics. Maldacena and Suskind's conjecture, they are the same thing. An entangled pair of particles is not just correlated. It is, in some precise geometric sense, connected by a microscopic wormhole. The quantum correlation and the space-time connection are 2 descriptions of a single underlying reality. Space is not just held together by entanglement. Entanglement is space. The geometry of the universe and the pattern of its quantum correlations are 2 languages saying the same thing. Now let's bring both threads together, because this is where the implications become truly vertiginous. If time is not fundamental but emergent, if it is what entanglement between subsystems looks like from the inside, and if space is not fundamental but emergent, if it is the geometric expression of quantum correlations, then both of the basic scaffolding pieces of the physical world, the stage on which everything happens, are manufactured inside the universe from quantum information. Space and time are not the container. They are the product. They are not given. They are made. And here is the consequence that follows as cleanly as anything in physics. If space and time are generated by the universe's own internal quantum structure, then the universe cannot predate its own quantum structure. There is no before the universe in which to locate an origin. The word before only makes sense inside a temporal framework, but temporal frameworks are things the universe produces. There is no external timeline in which the universe's creation could be scheduled. The universe does not exist within time. Time exists within the universe. And the same is true for space. The universe is not a thing that appeared somewhere and somewhen. Somewhere and somewhen are features of the universe, generated by the universe, and they do not extend beyond it. This means the question, what caused the universe to begin, contains a hidden structural error. A cause precedes its effect in time. That's what causation means. But if time begins with the universe, then a cause of the universe would have to precede time, operating in some timeless void before the first moment, which is not a description of physics. It's a description of nothing. There is no prior time in which a cause could exist. The question asks for something the structure of reality cannot accommodate. Not because we're too limited to see it, but because the machinery it would require an external timeline, a pre-existing causal stage, is exactly the kind of thing that quantum gravity says does not exist, which is, in a slightly different vocabulary, exactly the conclusion John Wheeler kept arriving at from every direction he approached. The universe does not have a cause outside itself, because there is no outside. The universe does not have a beginning in time, because time is something the universe generates internally. The universe is not in anything. Everything that could be in anything is inside the universe, including time, including space, including the structure by which causation itself is possible. And so the question of what created the universe is not answered. It is dismantled, not by giving up, not by retreating to mystery, but by following the physics all the way to the edge and finding that the edge is not a wall, but a loop. The universe does not create itself in the way a craftsman builds a chair, standing outside it, applying force across time. The universe creates itself in the only way it could, by being the totality within which creation, time, space, and the question itself all find their footing, by being, in Wheeler's phrase, a self-excited circuit, turning itself on, completing itself through every entanglement, every measurement, every correlation, the questioner and the question and the universe being questioned, the same thing, seen from the inside of something that has no outside. Every time you feel like you understand that, sit another moment with it. It'll keep going. Part 10. The Modern Battlefield. Quantum mechanics is almost a century old. It was formalized in the 1920s. It has been tested to extraordinary precision. It works. And yet, right now, in 2025, some of the most careful physicists alive cannot agree on what it means. Not what it predicts, everyone agrees on that. What it is actually saying about the nature of physical reality, what the theory is a theory of. This is not a minor gap in our understanding, the kind of thing that will be tidied up once someone runs the right experiment. It is the central unsolved problem in the foundations of physics. A foundational crisis that has been open for nearly 100 years and that has, if anything, become more acute as the experiments have gotten more precise and more extreme. And in the past 2 decades, something important has shifted. This debate has moved from being primarily a philosophical disagreement among specialists arguing in seminar rooms, the kind of thing most working physicists felt comfortable ignoring while they got on with their calculations, to an active area of experimental research with real, testable, measurably different predictions. The question of what quantum mechanics means has become a question physics is being forced to answer, whether it wants to or not. The reason this matters for everything we have been building tonight is that Wheeler's participatory universe, his claim that observers reach backward through cosmic history and participate in constituting physical reality, is not a claim that sits comfortably in any of the major interpretations of quantum mechanics. It sits at the intersection of all of them. And to evaluate it honestly, you have to understand what the alternatives are offering, and more importantly, what each of them is asking you to give up, because none of them are giving you reality for free. Every interpretation of quantum mechanics is a trade. You choose what you want to preserve, and you pay a price. The question is, which price you find least painful. Let's go through the main ones. The first is relational quantum mechanics, developed by the Italian physicist Carlo Rovelli, who is probably best known outside specialist circles for his popular writing about quantum gravity and time. Rovelli's central claim is this: quantum mechanics does not describe an objective, observer-independent physical reality that exists out there, complete and definite, waiting to be read off by any observer who happens to come along. Instead, quantum mechanics describes the state of one physical system relative to another. There is no absolute view-from-nowhere quantum state of a particle. There is only the state of the particle relative to a specific system interacting with it. And here, observer does not mean a conscious being. It means any physical system capable of recording an interaction, a detector, a mirror, a cloud of gas molecules, a bacterium. What this means in practice is that different physical systems can have mutually inconsistent facts about the same quantum event, and both can be correct. From the perspective of the system that interacted with the particle has a definite state. From the perspective of a system that has not yet interacted with either of them, the particle is still in superposition. Both descriptions are valid. Neither is more real than the other. There is no global, God's eye view of reality, in which all the facts cohere into a single, consistent picture. Reality, in Rovelli's framework, is irreducibly perspectival. It is always the state of something relative to something else. This handles the Wigner's friend paradox we looked at earlier with elegant economy. Wigner, standing in the hallway, and his friend inside the lab, each have valid and internally consistent descriptions of the experiment. They don't agree. That's fine. The theory does not require them to agree, because the theory is not describing a single global reality that they are both imperfectly perceiving. It is describing the relational facts between each of them and the systems they have interacted with. The contradiction disappears once you stop assuming there is one reality that both descriptions are supposed to be converging on. The cost of this move is significant. It requires giving up on the idea of observer-independent physical facts. There are no facts about the universe that exist independently of some physical system's relationship to some other physical system. Reality, on this view, is not a noun, it is a verb. It is always the outcome of a relationship, and that maps, perhaps more closely than any other mainstream interpretation, onto Wheeler's participatory universe. If all facts are relational, if reality is always constituted by interaction, then observers are not passively reading a pre-existing world. They are, in the most literal sense, participating in constituting it. The second interpretation worth understanding is quantum Bayesianism, called cubism, developed primarily by the American physicist Christopher Fuchs. Cubism takes a more radical step than Rovelli. It says the quantum state, the wave function, the central mathematical object of quantum mechanics, is not a property of the physical world at all, not even a relational property. It is an agent's personal belief about what will happen when they take an action on the world. When a physicist writes down a quantum state, they are not describing something out there. They are encoding their own expectations. When they make a measurement and update the state, They are updating their beliefs in response to a new experience. Nothing in the external world collapses. Nothing physical happens to the wave function. The wave function was never out there in the first place. This sounds like it should lead to solipsism, or at least to the conclusion that physics is just a tool for managing expectations rather than a description of reality. Fuchs resists this vigorously. Cubism is not the claim that the world doesn't exist. It is the claim that the world is richer and stranger than any description of it. When an agent makes a measurement, something genuinely happens. A new experience is created. The world responds. The world is not indifferent to the agents within it. It is shaped by their interactions with it. In Cubism's language, measurement is not discovery. It is creation. An agent reaches out, takes an action, and the world offers back a response that neither party fully controlled in advance. Fuchs talks about this in language that consciously echoes Wheeler. He considers himself Wheeler's intellectual heir on exactly this point. The participatory nature of reality in Cubism is not an accident or an embarrassing side effect of the formalism. It is the central lesson. The universe and its agents are not separate. Every interaction is a genuine contribution to what the world is. Not because your consciousness is projecting reality, but because the structure of physics does not allow a clean separation between the act of measurement and the world being measured. The cost of Cubism is intersubjectivity. If my wave function is my belief and your wave function is your belief, what makes our different beliefs about the same system compatible? Fuchs has worked hard on this question, and there are answers: the Born rule as a consistency condition on rational belief, coherence constraints on how agents should update, but critics find the framework hard to square with the scientific ideal of objective, communicable, publicly verifiable knowledge. Cubism works. It is internally consistent, but it places the individual agent at the center in a way that many physicists find uncomfortable. The third major framework is quantum Darwinism, developed by Wojciech Zurek at Los Alamos National Laboratory, and it takes a completely different approach. Instead of focusing on the relationship between an observer and a quantum system, Zurek focuses on the environment. His argument starts from a simple observation. The reason all of us agree that the cat is either alive or dead, rather than in a superposition of both, is not that any one of us directly collapsed the wave function by looking. It is that photons have been bouncing off the cat for milliseconds and carrying information about its state into the room, into the walls, into our eyes, into everything. The environment is constantly copying information about macroscopic systems into millions of redundant records. By the time you open the box, the answer is written everywhere. Zurek calls this process quantum Darwinism because it is a kind of selection. Of all the possible quantum properties a system could have, only certain ones, position, momentum, the properties we think of as classical, get copied into the environment in a stable, redundant way. Those are the properties that survive. Those are the properties that become real in the classical sense, because they are the ones being broadcast by the environment and received by multiple independent observers. We all agree the cat is dead because we are all receiving the same environmental signal about the cat's state. Classical reality, in quantum Darwinism, is not an illusion. It is the subset of quantum reality that the environment has selected and amplified into consensus. This is the interpretation most sympathetic to a kind of softened realism. It recovers something close to observer-independent facts without requiring hidden variables. The world has definite classical properties not because God set them in advance, and not because individual observers create them, but because the environment has done the work of selection and broadcasting. The observer's role is not to collapse a wave function, but to access one of the many environmental copies of already proliferated classical information. The cost here is subtler. Quantum Darwinism does not fully eliminate the observer's role. It just distributes it, spreading the measurement process across the environment instead of locating it in any single observer. And it does not answer the deep question of what determines the basis in which environmental copying occurs. Why position and momentum rather than some quantum superposition of both? The theory defers to decoherence, but decoherence, as critics point out, explains why quantum interference becomes undetectable without explaining why one definite outcome occurs rather than another. The hard core of the measurement problem is still there, just moved deeper inside the machinery. Now, all of these interpretations, relational quantum mechanics, cubism, quantum Darwinism, and the many worlds interpretation we discussed earlier, have to contend with the Frauchiger-Renner result. What Frauchiger and Renner showed, remember, is that if you assume quantum mechanics applies universally at all scales, including to observers, and if you assume observers can consistently reason about each other's measurements using quantum mechanics, you get logical contradictions. Two observers, each reasoning correctly from their own perspective, arrive at mutually incompatible conclusions about what happened. Each interpretation survives this result, but each survives by paying a specific price. Relational quantum mechanics accepts observer-relative facts and says the contradiction evaporates once you stop expecting global consistency. Cubism restricts the scope of quantum reasoning to individual agents and says the contradiction arises from an illegitimate step treating another agent's private experience as a fact you can reason about using the Born rule. Many worlds says all outcomes happen in branching universes, so there is no single what happened to contradict in the first place. Each response is coherent, none is cheap. Something must be surrendered, either global realism or intersubjective reasoning, or the uniqueness of measurement outcomes. The universe is forcing a choice, and the choice is non-trivial. Then there is one more position, sitting at the edge of the landscape, that deserves honest treatment, even though most physicists find it unacceptable. It is called superdeterminism, and its most vocal recent advocate is the theoretical physicist Sabine Hossenfelder. The argument goes like this. Bell's theorem, which we covered earlier, is not just a mathematical result. It depends on an assumption, the freedom of choice assumption, also called statistical independence, which says that an experimenter's choice of measurement setting is independent of the hidden state of the particles being measured. If that assumption is false, if the experimenter's choice and the particle's hidden state were correlated from the very beginning of the universe, pre-encoded into the initial conditions of the Big Bang, then Bell's inequality violations can be explained without any quantum weirdness. Hidden variables survive, realism survives, locality survives. The apparent strangeness of quantum mechanics is an artifact of not noticing that everything was already connected at the start. The cost is catastrophic for science itself. Without freedom of choice, the methodology of controlled experiments collapses. Any result can, in principle, be explained by claiming that the experimenter's choices were pre-correlated with the outcome from the moment of cosmic origin. Superdeterminism can explain anything. A theory that can explain anything predicts nothing distinctively, which means it is not falsifiable, which means it has exited the domain of empirical science. Most physicists consider this price so high that superdeterminism functions more as a limiting case that shows how far the alternatives can go than as a live research program. What emerges from this landscape is a picture that should feel both clarifying and humbling. Physics has reached the point where its foundational questions are no longer deferrable. The experimental tests are tight enough, the theoretical constraints are tight enough, that the different interpretations are beginning to make measurably different predictions in edge cases, extended Wigner's friend scenarios, certain quantum gravity contexts, future Bell tests of increasing sophistication. The question of whether reality is observer-relative, information first, environmentally selected, or something else entirely, is not a question about the philosophy of physics. It is a question about physics, with experiments being designed right now to probe exactly this. And Wheeler's central claim that the universe constitutes itself through the chain of measurements within it sits at the intersection of every one of these competing pictures. Some accept it wholesale. Some approach it obliquely. None of them make it go away. The measurement problem and the participatory universe are, at the end of the day, the same problem seen from two directions, and neither one is finished. Part 11. The misinterpretations. This is the part of the conversation where things tend to go wrong, and I want to be careful here, because the ideas we have been building all night are genuinely strange, and genuinely strange ideas have a gravitational field all their own. They pull certain conclusions toward them. They attract certain kinds of minds, and the conclusions that get pulled in are almost always more comfortable than the physics actually warrants. So, let's do something a little different for a moment. Instead of building towards something, let's clear some ground. Let's talk about what the experiments we've described tonight do not mean. Because the misreadings are so common, so persistent, and so confidently stated in certain corners of the internet that if I don't address them directly, someone is going to walk away from this video with exactly the wrong lesson. And that would bother me more than I can reasonably explain. Here is the pattern. The moment you say, in any public forum, that observers affect reality, that measurement creates physical facts, that the act of observation participates in constituting the universe, a certain kind of mind hears something very different from what was said. They hear an invitation. An invitation to conclude that consciousness creates reality, that positive thinking reshapes the physical world, that the universe is fundamentally responsive to human intention, that quantum mechanics, finally, after all these years of being complicated and inaccessible, has come through and validated the belief system they were already carrying: quantum healing, the law of attraction, the simulation hypothesis, the idea that you can, with sufficient mental focus, alter the outcomes of physical events. None of this is supported by the physics. Not a single experiment we have discussed tonight points in that direction, and I want to explain, carefully and specifically, why. Start with consciousness. The claim that consciousness plays a special role in quantum mechanics, that the wave function collapses when and only when a conscious observer looks, has a real historical entry point in physics, which is part of why it persists. Eugene Wigner, one of the great physicists of the 20th century, Nobel laureate, the man who gave us the Wigner's friend thought experiment that we spent considerable time on earlier, Wigner did, for a period of his career, holds something like this view. He genuinely entertained the possibility that consciousness was the thing that triggered wave function collapse, that the chain of physical interactions could only terminate in something definitively non-physical, namely the subjective experience of a mind. He wrote about it. He is cited for it constantly. What is almost never mentioned is what happened next. Wigner thought about it more, engaged with the philosophical and physical objections, and changed his mind. He retracted the interpretation. He found it philosophically untenable. The idea that consciousness was a special causal agent operating on physical systems ran into problems he could not resolve, and he withdrew it. The man most responsible for introducing the consciousness causes collapse idea into serious physics decided it was wrong and said so. This is how science is supposed to work, and Wigner deserves credit for it. But the retraction rarely makes it into the popular account, because a Nobel laureate saying, "I was wrong about this," is much less exciting than a Nobel laureate saying, "Consciousness might be the engine of reality." The current status of consciousness causes collapse. In the community of physicists, who actually work on quantum foundations, is not controversial but possibly correct. It is not an open question. It is no experimental support, not falsifiable in most of the formulations it gets stated in, and not a live option in any of the major research programs we walked through in the previous section. Relational quantum mechanics does not need consciousness. Cubism is about agents, not minds. The distinction matters, because an agent in cubism is a physical system that takes actions and has experiences, not necessarily a conscious one in any philosophically loaded sense. Quantum Darwinism explicitly argues that the environment does the relevant work, with no observer required at all in the biological sense. Many worlds has no collapse whatsoever. In none of these frameworks does the presence or absence of conscious experience make any difference to the physics. When physicists use the word observer, they are not using it the way you might use it in conversation. They are not talking about a person standing at a window. An observer, in the quantum mechanical sense, is any physical system that becomes correlated with another physical system in a way that registers information about it. That is the complete definition. A photomultiplier tube is an observer. A Geiger counter is an observer. The air molecules drifting through your room right now, bouncing off the walls and carrying away tiny records of every surface they contact, are functioning as observers continuously and indiscriminately. The universe is full of observers in this sense, has been since the first microsecond after the Big Bang, and none of them are conscious. None of them are biological. None of them care. Consciousness is not a requirement. It never was. The word observer in quantum mechanics is a technical term that borrowed ordinary language and used it for something more general, and that borrowing has caused a century of confusion that shows no signs of abating. Now let's talk about the simulation hypothesis separately, because it gets conflated with Wheeler's informational ontology so often that the two ideas have almost merged in popular discussion, and they are genuinely not the same thing. The simulation hypothesis, in its standard form, claims that the universe as we experience it is a computation being run by some external intelligence on some kind of substrate. There is, in this picture, a reality outside our reality, a more fundamental layer where the computers live, where the programmers operate, where the actual physical substrate of existence resides. Our universe is an output, a render, something being generated by something else that is more real than we are. Wheeler's it from bit is not this. It is not even in the same neighborhood as this. Wheeler was not suggesting that the universe is a simulation. He was making a claim about the fundamental ontology of the universe itself, about what it is made of at the deepest level, from the inside. His claim is that the basic stuff of physical reality is not matter or energy or space-time, but information. Binary distinctions. Yes or no answers to physical questions. That particles and fields and geometry all emerge from the accumulated outcomes of interactions, each of which registers a bit of information. This is a claim about structure, about what the universe is made of in itself. It says nothing about an external computer. It says nothing about a programmer. There is no outside layer in Wheeler's picture. There is no simulator. The universe is the computation, not a simulation of something else, the actual process of reality constituting itself through information. The universe is not being run, it is running. There is a categorical difference between these two ideas, and collapsing them does a disservice to both. The law of attraction deserves direct treatment because it is the most practically consequential misreading, the one that has sold the most books and done, arguably, the most damage. The claim, in its various forms, is that human mental intention literally shapes physical outcomes, that focused positive thought can alter the behavior of matter and energy in ways that benefit the thinker, that the universe is, in some operational sense, responsive to what you want. This has been tested. The Princeton Engineering Anomalies Research Laboratory, known as PEER, spent several decades from the late 1970s through the mid-2000s attempting to detect statistically significant influences of human intention on random physical processes. Electronic random number generators, mostly. The results they reported were small, contested from the start by statisticians who looked at the methodology, not replicated by independent laboratories using comparable designs, not significant at the level that would be required to constitute scientific evidence. The program ended, and the effect, to the extent it was ever real, has not survived independent scrutiny. But even setting aside the specific experimental record, there is a more fundamental reason why the law of attraction is not what quantum mechanics supports. The change that quantum measurement produces the selection of one definite outcome from a superposition is random. Not random in the sense of, we don't know what's happening. Random in the sense that the Born rule gives you probabilities, and the actual outcome is not determined in advance by anything, including the measurer's preferences. The measurer has control over one thing only: which question is asked, which property is measured, not what answer comes back. You can choose to measure spin along the vertical axis, but you cannot choose whether the result is up or down. The outcome is not yours to direct. It belongs to the universe, and the universe, in this respect, is not taking requests. What quantum mechanics actually supports is something more precise, less comfortable, and if you sit with it long enough, significantly stranger than anything the self-help industry has managed to propose. It is not that the universe responds to your wishes. It is that the boundary between you and the universe is not where you think it is. That the distinction between observer and observed the line you intuitively draw between yourself and the thing you're looking at is not a sharp line at the physical level. That interactions constitute reality rather than merely revealing it. That the chain of physical interactions running through the universe, including every interaction occurring in your body right now, is part of what makes the universe physically real. That you are not a witness to a reality that exists independently of you. You are a node in the network through which reality constitutes itself. That is a radical idea. It does not need to be inflated into mysticism to be radical. It does not need to be dressed up as cosmic responsiveness to human intention. It does not need to validate any prior belief system. It is radical on its own terms, in its own language, with its own experimental support. And the inflation, the packaging of genuine quantum weirdness into spiritual comfort food actually obscures the radicalism. It makes the real implication harder to see by replacing it with something more palatable and less true. The real implication is stranger than the universe listens to you. The real implication is that the universe has no sharp inside-outside boundary between the listener and the thing being heard. And that is not a warm, reassuring thought. It is a vertiginous one, which is probably why it keeps getting replaced. Part 12. The 4 possible answers. Let us come back to the central question now. After everything we have built tonight, the measurement problem, the Bohr-Einstein argument, Bell's theorem, the delayed choice experiment, the quantum eraser, Wheeler's U-diagram, the holographic principle, the emergence of space-time from entanglement, the landscape of competing interpretations, let us try to state the question as cleanly and precisely as we can, because it deserves that. It has earned that. The universe is, at its most fundamental level, a quantum system. That is not a philosophical position. That is the conclusion of a century of increasingly precise experiments. Quantum mechanics is the framework within which everything we know about matter, energy, and their interactions is described. And it works to a degree of accuracy that no other scientific theory in history has matched. So when quantum mechanics says something about the fundamental nature of physical reality, we should take it seriously, especially when what it says is uncomfortable. And what it says is this: quantum systems are not fully definite until they interact with other systems, until they are measured in the broad physical sense of that word. Before measurement, a quantum system exists in superposition, a combination of possible states weighted by probabilities without a single determinate fact about its properties. Measurement creates definiteness. This is not an interpretation. This is the core operational content of the theory that every working physicist, regardless of their preferred interpretation, uses every day. Now apply that to the universe as a whole. The universe began approximately 13.8 billion years ago in an extraordinarily hot, extraordinarily dense state we call the Big Bang. For the first several 100 million years of cosmic history, there were no structures complex enough to perform anything we would recognize as observation. No galaxies, no stars, no planets. No chemistry above the simplest atomic level. No life, no instruments. Just an expanding plasma of particles and radiation, slowly cooling, density variations growing under gravity, the universe feeling its way towards structure through a process that had no one watching it. The question that follows from taking quantum mechanics seriously at cosmological scales is not rhetorical, it is not poetic. It is a concrete physical question with real stakes. What completed the universe's quantum states during that period? What made the early universe definite? What resolved the superpositions of the primordial cosmos? And the deeper question that follows from that one, does the answer imply that the universe's existence is, in some physical sense, self-constituted? That it creates itself through the chain of interactions that its own evolution eventually generates? There are 4 serious answers to these questions, not vague philosophical positions. Actual physical frameworks with different mathematical structures, different implications, and in some cases, in some regimes, different experimental signatures. We are going to walk through all 4 because no honest treatment of this topic can pick one and ignore the others. The question is genuinely open. The uncertainty is real. And understanding the shape of that uncertainty is part of understanding what kind of question we are actually asking. The first answer is the most dramatic, and it is the one most directly connected to everything Wheeler spent his career arguing. Call it the Wheeler strong form. This is the literal self-creation interpretation. The participatory universe taken at full strength, without qualification, without pulling back from the edge. In this picture, the universe genuinely is a closed causal loop. Observers in the present, and again, not just human observers, but all physical systems capable of interaction, every particle collision, every photon absorption, every quantum correlation being registered anywhere in the cosmos right now, reach backward through time, through the mechanism of quantum correlations, and participate in defining events in the cosmic past. The past is not a sealed record sitting in a vault. It is still being finalized. Every measurement occurring now is adding the last entries to a ledger whose earlier pages were left deliberately incomplete. The U-diagram Wheeler drew is not a metaphor or a loose analogy. It is his description of the universe's actual causal structure. The future participates in creating the past. The past creates the conditions for the future. The structure is self-consistent, self-referential, and in the only sense the question can meaningfully be asked, self-creating. The logical architecture underlying this is sometimes called a self-consistent loop or a bootstrap universe. It connects to John Cramer's transactional interpretation of quantum mechanics, in which quantum events are not described by a wave function propagating forward in time alone, but by a handshake between a wave moving forward in time and a confirmation wave moving backward. A quantum event, in this picture, is not a one-directional transaction. It is a negotiation between future and past that results in a consistent agreement. The present measurement and the past event reach toward each other and lock in, The transaction completes across time rather than within it. It also connects to one of the most remarkable proposals in all of theoretical cosmology, the no-boundary proposal of James Hartle and Stephen Hawking. Hartle and Hawking asked what happens when you apply quantum mechanics not just to the contents of the universe, but to the universe's geometry itself, to space and time as dynamical objects rather than fixed backgrounds. Their answer was that the universe does not have an initial, singular boundary condition. It does not have a moment of creation in the ordinary sense, a sharp edge where time begins, and before which there is nothing. Instead, the universe's history, traced backward in time, curves smoothly into a compact four-dimensional geometry with no boundary, the way the surface of a sphere has no edge. You can move in any direction on a sphere, travel as far as you like, and you will never fall off. In the Hartle-Hawking model, you can trace the universe's history backward, and you will never reach a singular beginning. The beginning becomes a smooth geometric cap, a region of imaginary time in the technical sense, with no sharp prior moment and no external cause. The universe is not preceded by anything, because the concept of preceded depends on a time coordinate, and the time coordinate smoothly ceases to be well defined before you reach any edge. The appeal of the Wheeler-Strong form is that it takes the experimental results of the last several decades seriously, the delayed choice results, the Bell violations, the Wigner's friend experiments, the informational nature of space-time, and follows them to their logical conclusion without flinching, without drawing an arbitrary line somewhere and saying quantum mechanics applies up to here, and then something classical takes over. The cost is genuine and significant. It requires accepting a kind of temporal non-linearity that is alien to everyday causality. It requires that the present genuinely influences the past, not just in the statistical sense that quantum correlations are non-local across space, but in the strong sense that the universe's past history is constitutively dependent on observations not yet made when that history was occurring. That is a hard pill to swallow. It asks for a revision of causality at the deepest level. The second answer accepts Wheeler's it from bit, the idea that the universe is fundamentally made of information but declines the retrocausal step. It says, yes, reality is constituted by information processing. Yes, measurement creates definiteness. But no, we do not need observers in the present reaching backward to complete the past. The universe is its own measurement apparatus, and it has been running continuously since the first microsecond. In this picture, the early universe's quantum states were resolved not by any future observation, but by the extraordinarily dense, hot, furiously interacting plasma of the primordial cosmos itself. Every particle collision was a measurement in the quantum mechanical sense. Every photon-electron interaction registered information. Every quantum fluctuation that left a tiny imprint in the density of matter imprints we can still see today in the cosmic microwave background, in the distribution of galaxies across the sky. In the large-scale structure of the universe, every one of those fluctuations was a measurement event. The universe has been measuring itself continuously and comprehensively from the very beginning. No special observers required, no retrocausation, no closed causal loops. Just the universe's own internal dynamics, churning through information, collapsing superpositions through environmental interaction and decoherence, building definiteness from the inside out. This picture connects naturally to quantum Darwinism, the framework where classical reality emerges from the environment's proliferation of redundant information copies extended to cosmological scales. The cosmic microwave background is, in a sense, the universe's earliest environmental record. It is the first large-scale redundant broadcast of information about the universe's state, written in the temperature variations of light that was emitted when the universe was 380,000 years old and has been traveling freely through space ever since. Every cosmologist who has ever mapped that background radiation has been reading a record that the universe wrote about itself nearly 13.8 billion years ago. The universe was keeping records before there was anyone to read them. The appeal of this picture is that it preserves something closer to the traditional scientific image of a universe that existed and did things before anything like an observer was present. It is less conceptually violent. It does not require you to revise causality. The cost is that it deflects rather than resolves the hard question. If information processing is what constitutes physical reality, then what is doing the processing in a universe with no external reference frame? Information processing, in the formal sense, requires a distinction between the processor and the thing being processed. If the universe is all there is, it has to be simultaneously the processor and the input. It has to process itself. This is not a logical contradiction. Circular systems do exist in mathematics and in nature, but it is not a fully transparent picture. The question of what grounds the self-processing of a universe that is its own only context is one that the information-first framework defers rather than answers. The third answer is the most epistemically disciplined and in some ways the most frustrating because it declines to play the game at all. It says, the question of what completed the early universe's quantum states is not a question quantum mechanics can answer, because quantum mechanics is not designed to answer it. Quantum mechanics is a tool for predicting the outcomes of experiments performed by observers on physical systems. It is a framework that requires, built into its very structure, a distinction between the system being described and the observer doing the describing. The moment you try to apply it to the universe as a whole, including all the observers, including the measuring apparatus, including everything you have stepped outside the domain in which the theory has a well-defined meaning, you are asking quantum mechanics to describe itself. Describing itself, and that is not a well-formed request. This is something close to the Copenhagen interpretation, generalized from the laboratory to cosmology. Niels Bohr was always insistent that quantum mechanics was a theory of experimental situations, not a theory of mind-independent reality. The wave function is not a description of what the world is doing when nobody is looking. It is a tool for calculating probabilities given a specific experimental context. Asking what the wave function of the entire universe was doing before any experimental context existed is, from this perspective, not a deep question. It is a category error. A question that sounds meaningful, but is using theoretical concepts outside the domain where they have content. The virtue of this position is its honesty. It does not overreach. It does not pretend that we have more theoretical traction on the universe's origin than we actually do. It is a clean acknowledgement that our best theories have a scope, and the universe's origin may be outside that scope. The cost is real and significant. It forecloses the inquiry. If the question of what completed the early universe is genuinely outside the scope of physics, then physics has a fundamental incompleteness, a hole at the center of the deepest question it can approach. And many physicists, confronted with that conclusion, find it not restful but motivating, not a place to stop, but a description of the problem that needs solving. The fact that our current tools can't reach the question is not an argument that no tools ever will. It is an argument for better tools. The fourth answer is a middle position, technically precise, that tries to preserve the deepest insights of the Wheeler strong form without requiring that the present literally causes the past in a way that violates the standard causal structure of physics. It is built on a framework called consistent histories, developed by Robert Griffiths and extended by Murray Gell-Mann and James Hartle again, working at the intersection of quantum mechanics and cosmology with a persistence that has produced some of the most important results in the field. The consistent histories framework says that quantum mechanics does not describe a single reality unfolding along a single timeline. It describes a space of possible histories, each of which is a sequence of events across time with probability assignments attached. A consistent history is one in which the probability assignments at each step are mutually consistent. They do not contradict each other. They do not generate interference terms that would indicate you're mixing incompatible descriptions. The actual universe in this picture is one of these self-consistent histories, not selected by an external agent, not collapsed by an observer, but simply the history that is consistent with its own internal structure from start to finish. In this picture, you do not need retrocausation to explain why the early universe was definite. You do not need observers in the present reaching backward. You need only the consistency condition. The universe's history was always the one that is consistent with its present state, because consistency is built into the formalism from the beginning. The universe did not become consistent after observers appeared. It was always the kind of history that permitted the present state of affairs, including the observers, including the experiments, including the questions being asked right now, because histories that did not permit these things are not consistent with the present state we are actually in. There is a self-selection structure here that is sometimes called anthropic reasoning, though that term carries baggage that obscures more than it reveals. The precise point is simpler. We are asking this question from within a universe that produced questioners. The only histories in which the question can be asked are histories that produce something capable of asking it. This does not explain why this history, rather than some other consistent history, is real. It does not resolve the deeper metaphysical question, but it dissolves the apparent paradox of the early universe's definiteness without requiring any exotic causal structure. The universe was always self-consistent. The self-consistency is not something that had to be imposed from outside, or achieved through a causal loop, or established by retrocausal measurement. It is what it means to be a possible history at all. This connects to a beautiful old idea in physics called the bootstrap, popular in the 1960s as an approach to particle physics, before the Standard Model arrived and provided a different kind of answer. The bootstrap principle said that the particles of nature are not fundamental building blocks with independently given properties. They are self-consistent structures, each constituted by its interactions with the others, the whole system held together by its own internal coherence without external scaffolding. The universe in Wheeler's picture works the same way, scaled up to everything. It is not resting on anything outside itself. It is not supported by a prior cause. It holds itself up through the consistency of its own internal relations. The way an arch holds itself up, not because something is pushing it from outside, but because each stone is pressing correctly against its neighbors. The universe is the cause of itself, not in the sense that it reaches back in time and makes itself happen, but in the sense that it is the self-consistent structure within which causation itself is possible. There is no experimental resolution between these four options yet. They are all consistent with the data we have. The differences between them would show up in regimes we have not yet been able to test, in more extreme versions of the Wigner's friend scenarios, the kind being designed right now in quantum optics laboratories. In quantum gravity contexts, where the structure of space-time itself becomes a quantum variable, possibly in cosmological observations sensitive to the quantum nature of the early universe's initial conditions, observations that the next generation of telescopes and interferometers might begin to probe. The frontier is real. The experiments are coming. What I want to leave you with is not a verdict. I do not have a verdict. No one does. What I want to leave you with is a feeling for the texture of the question, a sense of what it actually means, what it has cost to get this far, and what the experimental record of the last several decades has already established beyond reasonable dispute. We know that quantum mechanics is the most precisely verified theory in the history of science. We know that its predictions require abandoning the idea that particles have definite properties independent of measurement. We know that Bell's theorem rules out hidden variables, ruling out the comfortable picture in which the universe's history was always definite and we just didn't know it. We know that the delayed choice experiment demonstrates that past behavior is not fully determined independently of present measurement choices. We know that the Wigner's friend experiments show that facts about measurement outcomes may be observer-relative rather than globally consistent. We know that space-time geometry emerges from entanglement structure. We know that time, at the quantum gravitational level, appears to emerge from internal quantum correlations within the universe, rather than from any external temporal framework. Every single one of those facts points in the same direction, not toward mysticism, not toward the law of attraction or consciousness, creating reality, or any of the comfortable misreadings we walked through earlier, toward something more precise and more vertiginous than any of those, toward a picture in which the universe is not a pre-existing object with a fixed history that observers passively discover, toward a picture in which the universe is a process self-generating, self-completing, continuously self-defining through every interaction occurring within it. And the word that keeps appearing in every serious treatment of this process, from every direction physicists have approached it, is the word Wheeler chose 50 years ago: participation. The universe and its contents participate in each other. The observer and the observed are not cleanly separable. The inside and the outside are not cleanly separable. The now and the then are less separable than they seem. Right now, as you watch this, every atom in your body is interacting with the world, emitting and absorbing photons, exchanging electrons with neighboring molecules, entangling its quantum state with the quantum state of everything it touches. Each of those interactions is a measurement in the quantum mechanical sense. Each measurement is a small increment of definiteness added to a universe that is continuously, in the most literal sense, completing itself. The air on your skin, the light arriving at your eyes, the sound, if you are listening rather than reading, all of it is, in Wheeler's picture, part of the universe's ongoing act of self-creation, not metaphorically, physically, incrementally, right now. You are not watching the universe. You are one of the processes through which the universe watches itself. You are not a witness to a reality that exists independently, waiting patiently to be observed. You are a node, one of an unimaginably large number of nodes through which reality generates itself. Every interaction your body has with the surrounding world is a tiny vote in the ongoing election that is physical reality. And Wheeler's most vertiginous claim, the one he kept returning to, the one he could not shake, the one that made even his colleagues uncomfortable, is that this process is not separate from the universe's origin. That the Big Bang is not something that happened once, concluded, and then produced a universe that then produced observers that then asked questions about it. The Big Bang, the universe, the observers, the measurements, and the act of asking this question tonight are all part of the same self-consistent, self-completing, causally looped structure. The beginning is not behind us, sealed and finished, receding into the past. The beginning is woven into the present. Every measurement is, in some precise physical sense, still writing it. I cannot tell you which of the four answers is correct. I genuinely do not know. I do not think anyone does. But I can tell you something I am sure of. This question is not closed. It has experimental content. It is being worked on right now with increasing precision and increasing urgency by some of the most careful minds in physics. And the question that may ultimately be forced on us by the experiments, by the mathematics, by the relentless pressure of taking quantum mechanics seriously at every scale is not which answer is right, but whether the question itself is the right kind of question. Whether we are asking what caused the universe, or whether we are slowly realizing that the universe is the kind of thing for which cause is not the right category. Whether asking what created the universe is like asking what is north of the North Pole. Not unanswerable because we lack information. Unanswerable because the concept does not extend to the domain in question. Maybe causation is something that happens inside the universe, between events embedded in the time and space the universe generates from its own entanglement structure. Maybe the universe is not something that was caused. Maybe it is simply the self-consistent, self-completing structure within which all causes and all effects find their footing, the stage that generates its own scaffolding, the question that contains its own questioner, the loop that has no seam. Does the universe create itself? The honest answer is, we do not know. The more honest answer is, we may be among the events through which it does. And the most honest answer of all is that the boundary between those two statements, between the universe creating itself and us being part of how it does, may be exactly the boundary that physics, in the next century, is going to dissolve.